Hello. In the previous lecture, we saw SISO decoders, soft in, soft out decoders for repetition code and single parity check code. There were some interesting calculations we did. Maybe some of it was a little complicated. I think the most important thing is to understand how the SISO decoder works and how to implement it. That is sort of the focus of this code. But once in a while, it's also good to see where some of these things come from. Such intuition is good in debugging, etc. sometimes. Okay, so let's proceed a little bit more on that. So I want to summarize quickly what this SISO decoder does for the single parity check code. So that is the most important ingredient that we will use again and again in the later part of the course. Okay, so let me quickly summarize single parity check code. Or SPC code. Okay, I took the 3,2 example. So let me first do the 3,2 example. 3,2. So we had two messages, M1, M2, and this gets encoded into a code word, which is C1, C2, C3. How does the encoding happen? C1 equals M1, C2 equals M2, and C3 equals C1 XOR C2, right? So the overall parity is maintained here, and after this you do BPSK symbol by symbol transmission over the Gaussian channel, and then you get your received vector R. You remember this R we thought of as the belief itself. The channel LLR is like the R, and then the SISO decoder produces intrinsic, extrinsic, and then the total, right? So how does that work? So it produces capital L1, capital L2, capital L3. The input small l1, small li is 2 times 2 by sigma square times Ri. This is the channel LLR. We saw this derivation in the last class, and then there was this function f of x, which was log tan hyperbolic modulus of x by 2. Okay, and then we saw that this capital L1 is going to become small l1 plus lx1. In fact, the same thing happens for everything. L2 plus lx2, and L3 is L3 plus lx3. And then what is each of these lx1s? So the lx1, okay, we describe the sign separately and the absolute value separately. The sign is sine of L2 times sine of L3, right? And then the absolute value is given by f of L2 plus f of L3. Okay, so in the decoder for the calculation of L extrinsic, the function f is involved. So this f of x is log tan hyperbolic of x by 2, and I put absolute value here. And one more thing to keep in mind is tan hyperbolic is something that's going to go less than 1. So log of that will be negative, and we want f to deal with positive values. So we'll put an absolute value around it. Okay, so this is the definition of f of x. There is an absolute value around the log tan hyperbolic as well. Okay, so once you make this definition, this is fairly straightforward to see. The absolute value of lx1 is f of L2 plus f of L3, and the sign of lx1 is product of the two signs. Okay, so let's see what this function is and plot it and see how it behaves in MATLAB. Okay, so we're going to go there. So let me go to my MATLAB screen. So first thing we'll do is we'll define this function f, which is like I said, absolute value of log of tan hyperbolic of absolute value of x by 2. Okay, so that's the function f, and then one can define x in this range -5 to +5, and then you can plot of x and f of x. Okay, and you can see how it works. And let me show you a slightly zoomed up version of this window, assuming I can get it to work. Yeah, there it is. And maybe I should get the axis on. Okay, and you can see how this works. So, as a function of x, this function f falls very steeply. Okay, for very low values of x, this function f is very high. Okay, and as x increases in value, this function falls quite steeply. So, even if you look at the value of f of 2, it's quite low. Okay, on the other hand, values of f close to 0 are really high, 3 and 4 and all that. Okay, so this gives you an idea for how to approximate f. Okay, in case you want to do a simple calculation, it's a nonlinear function. So, if you want to approximate f, one sort of simple thing to do is tend to give importance to the dominant values based on the argument. Okay, so if f of x, if x is very small, then f of x is very large. Okay, if x is slightly larger, then f of x becomes very small. Okay, so using this, one of the very popular approximations for this kind of calculation is, if you have f of L2 plus f of L3, this is approximately f of min of absolute value of L2, absolute value of L3. Okay, so because remember what I told you, this f function, when the argument becomes large, f of x, when x is large, becomes very small. Okay, so out of L2 and L3, whichever is smaller in absolute value is going to dominate the sum f of L2, f of L3. Okay, so f of L2 plus f of L3 is dominated by the minimum of the two values. So, f of min of absolute value of L2 comma absolute value of L3 is a good approximation. Okay, so this is once again, it's approximate, it's not exact, but it's a nice approximation. The reason is, once you make this approximation, absolute value of Lx1 has this very simple expression, f of min of absolute value of L2, absolute value of L3, and we know that f is its own inverse, f of x is x itself, and so this will just become min of absolute value of L2 comma absolute value of L3. So, this approximation is called the min sum approximation, and it's very popular in all implementations of this kind of extrinsic calculation. Okay, instead of looking at log, tan, hyperbolic and all of that, we can simply look at the minimum of those two values. So, if you want to do f of L2 plus f of L3, you look at the min of L2, L3, okay, and then simply take that as the Lx1. Okay, so it's a much simpler calculation than doing the nonlinear log, tan, hyperbolic and all that. Okay, simply minimum of absolute value of L2 and absolute value of L3. Okay, so this min sum approximation is quite a bit popular. So I want to maybe illustrate that a little bit in MATLAB. Okay, so to illustrate how this approximation works, so let's look at some received values. So I'll consider received values of this form 1 plus, I'll put a noise variance here, maybe the noise variance is 0.9 or 0.8 or something. Okay, and then a random noise 1 comma 3. Okay, so this gives me 3 received values. You can see the first two are greater than 1 and the last one has gone negative. So, there is some error, etc. Maybe we will consider one more. Okay, so this is going a little bit high. Yeah, but this should be fine. Okay, so this is a good received value. I didn't want to have some error in the value, so I'm picking some other value here. So next first step is to calculate the channel LLR. If you remember, the channel LLR is 2 by sigma squared. The sigma I've picked here is 0.8. Okay, 2 by sigma squared times r. Okay, so this is the channel LLR, and you can see it has a slightly larger value. So it goes to 2, 3, and 12. Okay, now let's illustrate what happens in LX1 calculation. So if you look at LX for the first one, okay, so this is going to be the sign is going to be the product of the signs of L2 and L3. So in this case, both L2 and L3 are positive. So you see L2 and L3 are positive. So the sign becomes just positive. So the sign of LX1 is positive. So LX1 comes out to be f of L of 2 plus f of L of 3. Okay, So, that is the answer. Okay. So, if you want to look at the calculation closely, f of L of 2 became 0.03 and f of L of 3 became something into 10 power minus 5. Okay. So, like I said, if you look at it, L of 2 is much smaller than L of 3. So, the minimum value of these two is dominating the calculation. Okay. So, that is what you got, and no wonder the Lx1 is so close to the min of L of 2 comma L of 3. Okay. So, you see both of these are really close. Okay. So, now Lx1 is the not the only thing you will compute, you will also compute Lx2, isn't it? Lx2 is once again all three L's are positive. Okay. If you look at the value of L again, all of the three L's are positive. So, the sign becomes positive throughout, sign of L1 into sign of L3 is also positive. So, if you want to compute Lx2 in absolute value, this is simply f of L of 1 plus f of L of 3, isn't it? This is the formula we saw before, and once again this you can see is very close to the minimum value. It is 2.04 and then 12.07. Really that f of L of 3 does not contribute anything, it goes to 10 power minus 3. On the other hand, if you look at Lx3, you see it is a little bit more difficult because L of 1 and L of 2 are close to each other. Okay. So, but let us see what we can do here. If you do this, you get something close to 1.9. Okay. So, it is not too bad, it is sort of close to 2, but not that close, it is away by like 0.1 or something like that, but that is something we can live with. Okay. So, this approximation of f of L1 plus f of L2 by the minimum of absolute value of L1 L2, it is a very powerful approximation. It simplifies the decoder in many ways, and in fact all practical decoders more or less use this min sum approximation. Okay. So, there are some modifications to the algorithm. Sometimes the people approximate the min sum using this offset min sum method, but let us not worry too much about that. For now, this approximation is very useful. Okay. So, let us go back to the picture we had. We are going to approximate the absolute value in this fashion. Okay. So, I am going to show also maybe one more illustration for what happens when there is an error. Okay. So, overall if you look at Lx1, if you look at the value of L and Lx1, Lx2 and Lx3, so you can see what has happened here. So, you see the first extrinsic LLR is the minimum of the second and third. Okay. So, first one is the minimum of the second and third. The second one 2.04 is actually the minimum of first and third, and the third one is roughly close to the minimum of first and second. Okay. So, it is sort of close to the minimum of first and second, not exactly equal, but it is roughly close. Okay. So, finding the minimums is a good idea. Okay. So, let us try to do one more case where things maybe are a little bit more difficult. Okay, there it is. So, this is a received value where there was one error. Okay. So, notice what has happened, I transmitted 111, okay, three values 111. The first one had no error, the second one has an error. Okay. Second one has an error, the third one has no error. Okay. So, now what happens in the decoding is when you try and decode the second bit, okay, you will go wrong, right. So, because it's already gone negative. So, if you just do a threshold decoding, you're going to decode that this is -1, on the other hand this is actually +1. Okay. Now, let us see how this capital L1, capital L2, capital L3 calculation goes, and we will use the min sum approximation. So, this Lx, okay. So, you need three values here, and remember once again the sign also matters. Okay. The sign matters as well. So, Lx1 is the sign of L of 2. Okay. So, first calculation is L equals 2 by sigma squared. So, we got the LLR, channel LLR. The next calculation is for Lx1. So, now the sign I have to take care of, sine of L of 2 multiplied by sine of L of 3, and then multiplied by the absolute value. For the absolute value, I can use the f function, or I can use the min function, min of ABS of L of 2 comma ABS of L of 3. So, there you go, that is Lxt1. So, the extrinsic LLR for the first bit is minus 2.4. So, you can see it is sort of close to this the minimum value that you have. Okay. So, if you want to do Lx2, you can take this first Lx1 expression and sort of modify it. Lx2 will be sine of L of 1, L of 3, absolute value of L of 1. So, again it is 10.04, it is sort of close to, both the values are close to each other, but nevertheless we are taking min. Okay. And then Lx3 is sine of L of 1, L of 2, absolute value of L of 1, L of 2. Okay. So, once again it is minus 2.4. Okay. So, we had L and the extrinsic LLRs Lx1, Lx2, Lx3 is this, and the total LLR is L plus Lx1, Lx2, Lx3, and that will come out as positive. Okay. So, we saw that the initial channel LLR gives you a negative value for the second bit, okay, but after you have done the processing you got positive values throughout and the error is corrected. Not only that, you got very high values for the output LLR. So, you have a lot of belief that these values are correct. Okay. So, this was a simple illustration of two things. First, how the single parity check decoder works, the SISO decoder works. You have received values, you convert them into LLRs, and then you use this F function and do some nonlinear calculation, you get one decoder, or you do this approximation, the min sum approximation, and we see that the beliefs get updated very nicely. The channel LLR gets updated with this extrinsic LLR and you get an output LLR capital L as we showed here, and these tend to be very good. Now, you can repeat this for other received values as well and see how this works to get some more intuition. I also showed you how the function f is sort of grows very rapidly. So, you have to only look at falls very rapidly, I am sorry, the function f falls very rapidly. So, you have to only look at lower values of the argument of the function f. Okay. So, as far as this lecture is concerned, I will stop, and in the next one we will see how to extend the same idea for the single parity check code SISO decoder to larger number of bits in the code word. So, instead of 3,2, supposing I have 10,9 or 8,7, how does the same idea work? Okay. So, we will do that in the next lecture.